Hey guys, Mr. O'Sullivan here. Hope you're doing well. Hey, welcome to 5 days to a Sixsky. This is day number one. And on this recording, we're going to talk about limits, continuity, and three major theorems. There's a link in the description below to the PDF that I'm using right here. So if you want to download that, follow along, anticipate kind of what we're doing here. All right. Well, first thing, definition of a limit. Well, we can think of a limit a lot of ways, but kind of a working man's definition, we could say that a limit is a particular y value that a function approaches as the function approaches a particular x value. And if we're talking about a two-sided limit, then that function approaches the particular x value from the left and the right. Of course, the exceptions to that, if we're just talking about a one-sided limit, or if we're talking as a limit of f of x as x approaches positive infinity, obviously, we're only going to be able to approach positive infinity from the left. Only God can approach positive infinity from the right side. Okay. For a two-sided limit to exist, the one-sided limits must be equal. That's a good fallback if we're ever asked to show that a two-sided limit exists. If we can show the one-sided limits are equal to each other, we're good. 5 ways to evaluate a limit. Okay. Well, first one, plug and pray. Algebraically, probably ought to do that one, use that one first every time. X is approaching 2, plug in 2 to the expression, see what happens. You might get a number, you might get an indeterminate form, meaning you got more work to do, or you might get, 7 over 0. That means the limit does not exist. Second way to evaluate a limit, L'Hopital. So again, if you plug and pray and you get indeterminate form, I go straight to L'Hopital. Third way, graphically, looking at the graph of a function or an expression. Fourth way, numerically, using a table, Mabel. And the third way, everybody's favorite, squeezy. Okay, 4 and 5 are rarely used, but we know about them. Okay, if f of x as x approaches c from the left is equal to infinity, and the limit of f of x as x approaches c from the right is equal to negative infinity, then we know that f of x has a vertical asymptote at x equal to c, and it would look like this variety. If the limit of f of x as x approaches infinity is k, then f of x has a horizontal asymptote at y equals k. Okay. 3 conditions necessary for f of x to be continuous at x equal to c. This is big. A lot of times the way they'll test this is with a piecewise defined function, and they're asking you if the function is continuous right at the point in its domain where it changes from one branch to another. All right, so the first condition is that the function's defined at that particular x value c, so f at c exists. Second one is the two-sided limit as x approaches c, f of x, that exists. And the third condition is those two have to equal each other. If they both exist and they don't equal each other, then we've got a hole at x equal to c. Okay. If f of x is blank, then f of x is also blank. Okay. If f of x is differentiable, then we also know that f of x is also continuous. At a point or on an interval, that holds true. The contrapositive of that is also true. If f of x is not continuous, then we know that f of x is also not differentiable. Again, at that point or on that particular interval. Okay. All right. Now we've got three important theorems. IVT. If f of x, first condition, f of x is continuous on the closed interval a to b, most popular condition, shows up a lot. And if k is betwixt and between f at a, I like to put f at a equals blank. Remind myself that if this is part of an FRQ, I need to show the value of f at a and f at b. So if k is between those two, the y values really at our endpoints, then by the IVT, we can conclude there is at least one, maybe a boatload, but at least one specific x value c in the open interval a to b, break me off a piece of that such that bar, such that f at c is equal to k. IVT. Okay, mean value theorem for derivatives. Well, has the exact same first condition of the IVT. Duplicate, don't hate. Bring that down. So if f of x is continuous on the closed interval a to b, and second condition for the mean value theorem, just change two things. If f of x is differentiable on the open interval a to b, then we can conclude by the MVT, then there is at least one x equal to c. Where does it live? In the open interval a to b, such that, I'm going to use the old such that bar, such that f prime of c, the derivative at that particular x value, is equal to the average rate of change, f at b minus f at a over b minus a. So f prime of c is equal to f at b minus f at a over b minus a. Or we could say the derivative at that particular x value c is equal to the average rate of change, or the instantaneous rate of change is equal to the average rate of change at the endpoints. And we could also say that the slope of the tangent line at that x equal to c is equal to the slope of the secant line at the endpoints. All right. EVT, extreme value theorem. If, any guesses? Yep, if f of x is continuous on the closed interval a to b, straight to the conclusion, then f of x has a maximum and minimum value on that closed interval. Think of that as an absolute max, absolute min. The absolute max can be equal to the absolute min if our function's a horizontal line. Okay. All right. Okay, let's go ahead and do some problems. All right. So this first one, the graph of f, I want to make sure I know what I'm looking at. It's a graph of f is shown above. What is the limit of f of x as x approaches 1? Well, going to obviously evaluate this graphically. Just, fingertip method. Fingertips aren't going to come together, so the limit does not exist. Okay. The left-hand limit would be 3. The right-hand limit would be 1. 3 is not equal to 1, so that two-sided limit does not exist. Okay. Okay, the next one looks like we've got a table. It says the function f is continuous. It's continuous and increasing for x greater than -1. Table above gives values of f at selected values of x. On the following, which is the best approximation for the limit as x approaches 0 from both sides, two-sided limit of e to the -2 fx. Okay, well, the only x that I've got in my expression that's approaching 0 from both sides is right here. So I'm going to go to my table and I'm going to look at my x values that are approaching 0 from the left and approaching 0 from the right. And then I'm looking at the corresponding y values. Well, it looks like my y values are going closer to 0. So if I plug that in for f of x, it's going to be the limit as x approaches 0 of e to the -2 times 0. That would be e to the 0, which is 1. Okay. Plug and pray, and that one had a little kind of twist to it where I also had to evaluate the limit numerically with the table. Okay. This one, couple ways you could go this. You could look at this one. If you recognize that's not just any limit, that is the limit definition of the derivative as a function. Well, we know that this is equal to d dx, whatever we have right here. So d dx of the natural log of x is equal to 1 over x. And then they tell us when x is equal to 2e. So now we just have 1 over 2e. That's a. If we didn't recognize it as the limit definition of the derivative, would have taken a little bit longer, would have evaluated it, maybe using L'Hopital, maybe subbing in the 2e for x here and here, and then using L'Hopital on that. We would have got plug and pray, would have got indeterminate form, and so L'Hopital would have been appropriate. Great. Moving on, moving on. All right. So this next one, the limit of this expression as x approaches 0 again from both sides. We do a quick plug and pray. It's not an FRQ, so I didn't need to write out and show that I'm evaluating the numerator separately from the denominator. But just plug and pray. I'm going to get 0. That would be e to the 0. That's 1 minus 0 minus 1. That'd be 0. So it's indeterminate. So I would bust out L'Hopital. So it's going to be the limit as x approaches 0. I take the derivative of the numerator. It's going to be 8x. Take the derivative of the denominator. That's going to be 4e to the 4x minus 4. I'm going to plug and pray again. I'm going to get 0. And I'm going to get 4 times e to the 0. That's 4 times 1 minus 0. So that's 0 again. So once more, L'Hopital. Can you keep using L'Hopital as long as we keep getting indeterminate form, either 0 over 0 or infinity over infinity are the two forms that we need to worry about. So now, again, the derivative of the numerator, d dx of 8x, that's going to be 8. Okay, right now, I know I'm not going to be doing L'Hopital again because I don't have 0 in the numerator, so there's no way I can get to an indeterminate form. So now I'm looking at the denominator. d dx of my denominator is going to be 16 e to the 4x. The 4 goes away. Now I'm going to plug and pray. So I'm going to get 4 times 0. That's 0. So e to the 0 is 1. So I'm going to get 8 over 16 or 1/2. Okay. All right. All right. Picking up steam. Okay. All right. This one, the limit as x approaches negative infinity of 3 plus 2 to the x over 4 minus 5 to the x. Okay. This one, I'm going to evaluate a little bit differently. What I'm going to do is I'm going to just plug into my expression kind of some negative numbers that are approaching negative infinity. So I'm going to start out with let's say -2. So I'm going to say x equal to -2. Again, I'm doing this because x is approaching negative infinity. So I'd get 3 plus 2 to the -2 over 4 minus 5 to the -2. And if I look at that, I'm going to have 3 plus, I can rewrite this as 1 over 2 over 4 minus, that's actually 1 over 2 squared. 4 minus 1 over 5 squared. Okay. Now I'm going to plug in another x as I'm approaching negative infinity. So now I'm going to do -10. Same thing. 3 plus 2 to the -10th over 4 minus 5 to the -10th. I can rewrite that as 3 plus 1 over 2 to the 10th over 4 minus 1 over 5 to the 10th. Okay, well, I think that's really all I need to do, because if I look right here, I can see that term in the numerator is going to be 1 over a larger and larger and larger number. And so that entire term is going to approach 0. So really that's going to go away. Same thing with that term in the denominator. And so as x is approaching negative infinity, that term is also going to go away. And so I'm going to be left with really 3/4. And that is my limit. Okay. That one a little tricky, but we can, we can sometimes always make sense of limits like that. As we're approaching a number, just put in successively numbers in that direction. Okay, let f be the function given by that function. For what values of x does f have a removable discontinuity, also known as a hole? So what we're looking for here is, do we have a common factor in both the numerator and the denominator? Well, first thing we need to do is factor, factor, factor. So if I factor out a 2, numerator, I got x squared plus 7x minus 8. Will that factor again? You betcha. That looks like it's going to be what? X plus 8 times x minus 1. Is that right? Looks good. And then in the denominator, again, I'm probably guessing maybe one of these factors, if I do have a hole, it's going to have to show up again in the denominator. So if I factor that, I'm going to have x, looks like x minus 8 and x minus 1. Okay. So now I'm kind of looking at those, and I do have a common factor. X minus 1 is the only common factor. Got to be careful. That's x plus 8, the numerator, and x minus 8, the denominator. So the only common factor is x minus 1, which means there's a hole at x equals 1 only. Okay. Cool. All right. All right. Moving on, moving on. Bada boom, bada bang. Okay. The graph of function f shown above on the following intervals, on which is f continuous but not differentiable. Okay, so it's the graph of f, and then they're asking me on the following intervals, where is f continuous but not differentiable? Well, that is kind of the definition of a cusp. That's a point on the function where it's continuous but it's not differentiable. Hey, there's the cusp right there. And then now I just got to find the interval. Looks like 2 to 3. Boom, right there. Okay. That one there, Time Banksky. Check it out. It's a calculator problem too. I have no idea. Calculator obviously isn't going to help you on that one. Okay. Moving on, moving on. Okay. Let f be a function such that f at 1 is equal to -2, f at 5 is equal to 7. Which of the following conditions ensures that f at c is equal to 0 for some value c in the open interval 1 to 5? Okay. As you read this is going to be dealing with one of our theorems, which the following conditions ensures that f of c equals 0. We might start seeing some familiar things here. For some value c in an open interval 1 to 5. Okay, that might remind us of maybe the conclusion to one of the theorems. And it's going to be, we might see, they're also talking about in the answer choices here, things about f is increasing, f is continuous. So really, we've got the endpoints. This is kind of like our f of a and our f of b. And 0 is our k value. And is k in between that, -2 and 7? Sure is. And so, yep, this is IVT. So we can remember the conditions for IVT. The second condition is that this k value is between f at a and f at b, or in this case, f at 1 and f at 5, and it is. 0 is between -2 and 7. The first condition is what? F has got to be continuous on that closed interval from 1 to 5. So that is the piece that's missing. But if that condition is also met, then we can ensure that there is a x equal to c in the open interval 1 to 5 such that f at c equals 0. Okay. All right. All right. Know those theorems. Okay. Next one. For t greater than or equal to 1, the position of a particle moving along the x-axis is given by p of t is equal to the square root of t minus 2. At what time t in the interval from the closed interval from 1 to 16 is the instantaneous velocity of the particle equal to the average velocity of the particle over the interval the closed interval from 1 to 16. Okay. Well, this one, we're basically asking, what's this time t in this interval from 1 to 16 where the instantaneous velocity of the particle is equal to the average velocity of the particle on the interval. Okay. So the what we've got to do basically is go through here and we're looking to find the instantaneous velocity. That's going to be p prime at t. So again, the position is given by p at t. Velocity is going to be the derivative of position. So p prime of t, that's going to be equal to velocity. And we look at that, we can do that. T to the 1/2, we'll rewrite there. So p of t, p prime of t rather, is going to be 1/2 t to the negative 1/2. And then we want to know when we're looking for this time where that is going to be equal to the average velocity of the particle on that interval from 1 to 16. So we're going to say, hey, this is equal to p at 16 minus p at 1 over 16 minus 1. Well, if we keep going with this, so p at 16 is going to be the square root of 16 minus 2 minus p at 1. It's going to be the square root of 1 minus 2 all over 15. So if I've got 1/2 t to the negative 1/2, my left side, and I simplify this, that's going to be 4, that's going to be 1. So 4 minus 2 is 2. 1 minus 2 is negative 1. 2 minus negative 1 is going to be 3. So I got 3/15 or 1/5. Okay. Now I'm just going to solve for t. So I'm going to multiply both sides by 2. So t to the negative 1/2 is equal to 2/5. And now I just want t. Well, I'd like it to be t to the first. And so I'm going to raise this to the negative second power, because negative 1/2 times negative 2 is going to be positive 1. So I'm going to get t to the first on the left side. What I do on the left, I got to do on the right. Well, what that's going to do, that negative is going to flip it. So I'm going to have 5 over 2 squared. So that's going to be 25/4. Want to double check that that is in my interval 25/4. That's what, 6 1/4? 6 1/4. And that is the interval in the interval from 1 to 16. Okay. So that would be the time in that interval where the instantaneous velocity of the particle is equal to the average velocity of the particle at the endpoints. Okay. That was mean value theorem for derivatives. All right. All right. Okay, guys, that's it for day one. Good luck, and good luck to you guys on all the other exams that you'll be taking. And we'll see you in a little bit for day number 2. Thanks, guys. Thanks for your efforts.